Well, welcome back. It's time now to talk about a few different topics, actually. I'll do at least two and then see how we go for time. The first topic is optimization, which is in Chapter 13 of the Calculus Lifesaver. We already did the second half of Chapter 13, which is linearization, earlier, so I'll skip that. But then move on to Chapter 14, which is about L'Hopital's rule, a different way of evaluating certain limits. If I have time, I'm going to start the introduction to integration. And that's going to occupy, integration's going to occupy us for the next few weeks. So, see if I have time. All right? So without much further ado, let's talk about optimization. Now, the word optimize means make good, or make as good as possible, in fact. So when we say good, this is math, so we're talking quantity over quality. Quantity is more important, so what's the best? Well, if it's, say, how much money someone is paying me, I think the best is to make it as big as possible. But if it's how much money I have to pay someone, I'd like to make it as small as possible. So we're talking maximization, minimization. We've already done this for functions. We did it last week, in fact, when we sketched curves, and even the week before we were looking at critical points. All this topic is can you use these techniques on word problems instead of just draw the graph of this? That's the entire topic. There's nothing else to it than that. Can you solve word problems using these techniques of critical points, maxima and minima, global and local, all that sort of stuff? All right, so I didn't quite present it like this in the book, but I think what I'll do is I'll just start off with the method. And then we'll look at a whole heap of examples, because there's nothing else to it than that, really. Practice, practice, practice. The first step is you've got some word problem that says, how do you make something as big as possible, or maximize something, or minimize something? Well, sometimes they give you variable names in the question, but a lot of the time, as in real life, there are no variable names. You have to pick them for yourselves. So I guess give names to variables. There might be only two, or there might be three, four, etc. If there's only one, you're in trouble, because you don't have any control. But there should be at least two variables. And one of these variables is important. It is the actual quantity you want to maximize or minimize. So identify the variable to maximize or minimize. And you might as well note whether you want to maximize it or minimize it. It should be quite clear from the wording. Okay, and you should write down something. You should say, let V be the volume of the so-and-so in cubic inches, or whatever the units are. So write out sentences here. It's a word problem. It deserves some sentences. Now you're converting it into math, of course. An often overlooked thing is try to get some feel. So get a feel for the domain of the variables. By the way, when I say identify the variable to maximize or minimize, for the moment I'm just going to call it Q, quantity. You can call it whatever you like. I have to call it something for this purpose of this. So in step 2, get a feel for all the input variables except Q, which is going to be the quantity that depends on the other variables. So you just got to say to yourself, okay, this is a length. It can't be negative. How short could it be? How long could it be? Maybe the question says the total length of fence is 300 feet. So there's no way that this length can be more than 300, or something like that. You'd like to try to get a domain for these variables, and you can do that by exploring the extremes. How large can it be? How small can it be? So step 3 is write down equations, or maybe one equation, relating the different variables. You may have to use geometry for that. It may be told to you in the question. Who knows? So step 4, you want to eliminate So eliminate all variables except 2. So somehow you have to solve these simultaneously. You want to get an equation that looks like Q equals function of just one variable. One of the variables there. That's what you'd like to do. You'd like it to be Q equals this. So this is the thing you're trying to maximize or minimize, and it's a function of the one variable, so in step 5 you can differentiate, and you get dq, d whatever the variable is, equals some function there. And you can use this to find the critical points. Remember, maxima and minima occur only at critical points or endpoints. And that is what we're going to use. Check each critical point and endpoints, if there are. Well, let's say both endpoints. And that's actually the whole point of step 2, to find the domain so you know what the endpoints are. So check each critical point and both endpoints, i.e. find the values of Q. Find corresponding of Q to find which one is biggest and which one is smallest. That's the same technique we used to find global maxima and minima earlier. But we also have 2 other techniques. Sometimes you can't find the endpoints as easily. So there are some other techniques. We have the table of signs for the first derivative. Remember, if you've drawn up a table of signs and it looks like this, this is at the critical point. If it's, say, positive and then negative, it's a maximum. And if there's only one maximum for the function in the whole place, in the whole real line, the whole domain, it is the global maximum, for example. And you can also see minimum is the other way around. You can also use the sign of the second derivative to help you. We'll see examples of all these different types of strategies, if you like. They're all sort of different tools that you need. Remember, if Q prime at the critical point C is positive, this means that the curve is concave up and you have a minimum. And again, if there's only one minimum, it must be the minimum. If, on the other hand, Q double prime of C is less than 0, it's concave down and you have a maximum. But beware. If Q double prime of C equals 0, you can't tell anything. It could be a max, it could be a min, or it might be a point of inflection. So that is the useless case. So this strategy here, using the second derivative to analyze the critical point, it works most of the time, but it does not work all the time. This one should work all the time, this first one here. But sometimes it's a pain to draw up the table. So it's nice to have different methods of finding the same thing. And finally, the last step is to then write a summary in words. And don't forget the units. It's not an acceptable answer to say R equals blah. That's the answer. You've got to say the radius of the can is so-and-so's feet or inches or whatever. Okay? And the other thing is just read the question and make sure that you've given the quantities that they want. For example, sometimes they will say, what is the area? What is the maximum area? And if you just say, oh, the dimensions are 3 by 4, well, you should lose a point because you haven't actually answered the question. The maximum area is 12 in that case, and it would be cubic inches or whatever. So answer the question. Okay? So this is the method for solving problems of a type that I've described but not even given any examples. So let's see, the next 50 minutes is probably going to be examples. But before I begin, maybe you have a question about this method. Maybe someone here. Yes?
What if there's an infinite number of maxima or minima?
Okay, so the question is, what if there are an infinite number of maxima or minima? Okay, the only way that would happen is if you're dealing with sine x or something like that on an infinite interval, in which case you're in some sort of trouble, perhaps. Hopefully the thing is periodic and you can just analyze it on one period and say, okay, well, then everything just repeats. But I can't think of a question where that's come up. Maybe you have one and then we can do it. We pray this does not happen. This is the disaster. As I say, I mean, that would be fairly exotic. Any other questions? All right. Well, let's look at some examples. What do I have? I have 3 examples. There's another one in the book, but I think the 3 examples will take us long enough and give us the idea. So let's start off with a fairly easy example. Suppose you have 2 numbers, not integers, just 2 real numbers, each no bigger than 8. But they sum to 10. So the question is, how big could the product be? How small? How big, how small for the product? Okay, so there's an answer. There's a question, rather, in words. The answer's got to be in words, but we've got to use some variables. So step 1 says we're going to pick some variables. Well, I don't know what you want to call the numbers. You can call them whatever you want. I'll just call them x and y. So let x and y be the numbers. No need for units in this question. They're just numbers. So step 2 says, and you don't need to write these numbers 1, 2, 3. I'm just writing those to be in parallel with what I had up there. Okay, so step 2 says, how big and small can the numbers be? Well, what do we know? Neither of them is bigger than 8. So we know x is less than or equal to 8, y is less than or equal to 8. But if we think about it, how low could the numbers be? I don't know, we've got to kind of think that the sum of them is 10. So if you think about it, how big could, say, x be? Well, it could be 8, in which case y would be 2. If x is smaller than 8, then y is going to be bigger than 2. So actually, you can't have any of the numbers less than 2, because if one of them was less than 2, the other one would be greater than 8. Okay, so actually, both the numbers are between 2 and 8. But we had to think about that. You know, that wasn't completely obvious from the question. It wouldn't be catastrophic if we forgot it. It wouldn't be a disaster. But it's nicer to understand this. Now, question part 3 says, write equations for the thing. Now, the problem is we didn't really finish step 1. X and y are the numbers, but what do we care about? We care about their product. So I've got to say, let P be their product. And that's actually the variable we want to maximize or minimize, depending on which part. So that's the important variable. So we have 3 quantities, P, the really important one, and then x and y. So we need equations. Well, clearly, P is x, y, since it's the product. And also, we have x plus y equals 10, because we know the sum of the numbers is 10. So we have 2 equations. We need to eliminate one of the variables, and I'll eliminate y. It doesn't really matter because the whole problem is symmetric. So from here, I get y is 10 minus x, and this means that P is xy, which is x, 10 minus x, which is 10x minus x squared. Okay, so there's P in terms of one of the variables x. Okay, so now step 4 says, well, that was actually step 4. 3 was to write down the variables. Step 5 is to differentiate. So if we differentiate this, we get dp dx is equal to 10 minus 2x, which we can factor if we like. It's not that important to do so, but what the hell, we'll do it. 2 outside of 5 minus x, and you may as well notice that that equals 0 when x equals 5. Okay, so we have a critical point at x equals 5. Now, for step 6, I've given you 3 possible methods, which aren't all guaranteed to work every time. But we have 3 possible methods to see whether 5 is a maximum, a minimum, to see what's going on. But I'll just show you what they all look like. I'll show you what they all look like, and you don't need to do all of these for this problem, but you can't just say, oh, well, 5 is a maximum or 5 is a minimum, because you don't know, right? In fact, we've got to solve both maximum and minimum, so who knows? We better check it out properly. So method 1, or I'll call it I, what we could possibly do is say critical point at 5, and the endpoints are 2 and 8. And we know that those endpoints from step 2 over there. Okay? So what we could just do is test the product using the formula P is equal to 10x minus x squared. So we could say when x equals 2, and we find P is 2 times 10 is 20 minus 4, 16. When x equals 5, P is 50 minus 25, which is 25. And when x equals 8, you can plug that in and see 80 minus 64 is 16. And of course, 2 and 8 give you the same answer, because the other number is 8 here or 2 here. So of course it's 16. Now actually, remember, maxima and minima occur only at endpoints or critical points. So these are the only possible candidates. And this immediately tells you that you have a maximum product when x equals 5, and we have a minimum product of 16 when x equals 2 or 8. And that's a proof. That's a proof. You're using the fact, as I say, that maxima and minima, global maxima and minima, must occur either at a critical point or at an endpoint. So all you have to do is check those values. We have 1 critical point, 2 endpoints, and that's it. Okay? So that actually gets both of them for us. If instead we took this dp dx, we had seen dp dx is equal to 2 outside of 5 minus x. So we could draw up a table of signs for this. Here's x, here's dp dx, and we'll keep our third row for little figures. We want to see what's happening at 5, which is the critical point. And we know that the slope is flat there. So we pick numbers a little less than, a little more than 5, say 4 and 6, although anything up down to 2 or 8, which are the endpoints, would work here. So dp dx here, we only care about the sign of it. When x equals 4, 5 minus x, the quantity is positive, so this is positive. And when x equals 6, 5 minus x is negative, so that's the table of signs. The slope is upwards here, the slope is downwards here, and actually, yes, x equals 5 is a maximum. So that actually tells us the maximum value is when x equals 5. It doesn't tell you what the maximum value is. You have to plug it in and find out that p equals 25 in that case. But it tells us that the maximum, whatever the graph of p versus x looks like, between 2 and 8, we know that there's only one maximum. So it's got to look like this somehow. We actually don't know what the minimum is. We don't know what the minimum is. It could be at 2 or at 8 or both. So you'd have to actually plug it in and find out, because you see this method only classifies the critical points. It does not tell you what's going on at the endpoints. And if there's only one maximum, where's the minimum? It must be either 2 or 8, or as it is in this case, both. So, see, it's not perfect, but I mean, it's given you a good idea at least of the maximum. But you still have to use the first method in this problem in order to get the minimum, because we need that for the second part of the problem. Finally, I'll show you an alternative method. If you just differentiate this again, so instead the second derivative, well, it's just minus 2, which is negative. Actually, you only need it to be negative when x equals 5. It's negative always. Doesn't really matter. The only thing that matters is whether it's positive or negative at the critical point. The fact that it's negative means it's concave down, which means, again, that x equals 5 is a maximum, a local maximum, again. This only shows a local maximum, this only shows a local maximum, but because it's the only maximum, it must be also the global maximum. Right? So again, once you've found this, you're in the same boat as you were when you've done this. You still find that you need to check the endpoints. So in this case, the first method is the simplest and the best. But there will be other examples where we'll see it's not quite like that. Sometimes 2 is the best, and sometimes 3 is the best. Anyway, we have finished the problem, except that we ought to write a summary. We know that the maximum occurs, so greatest product is 25 when the numbers are 5 and 5. Of course, x equals 5 here. Well, I'm not going to even write it. X equals 5. You have to solve for y to find the other one, and of course it's 5. And the least product is 16 when numbers are 2 and 8. It's no need to write or 8 and 2. I think that's okay. We can cope with 2 and 8 being the same as 8 and 2. All right? So, pretty simple problem. I made it a little harder by looking at 3 different ways, effectively, of step 6. But still, you do have to do something in that regard. Often, people will just leave it out. Yeah, got a question? Sure. Why did I choose to use the product as the other equation? Well, the question says, we got these 2 numbers. They add up to 10. How big could the product be? That's okay. That's okay. So that's why I chose the product. But it could be how big could the sum of the squares be, or the sum of the cubes. That would, in which case, you would use that instead of the product. No problem. Any other questions? That's okay. There's this. No problem. No problem. Right. Well, let's do something a little bit more difficult. So, for my second example, I'm going to assume that there is a farmer who's obsessed with right-angled triangles, because what he wants to do, he's got this wall here, and he wants to build a fence that is in a shape of a right-angled triangle with not the hypotenuse along this existing wall. I don't know why he wants to do this, but that's what he wants to do. And he wants to enclose some sort of field here. And he has 300 feet total length of fence. Is 300 feet. And the question is, what shape should he make this right-angled triangle here in order to maximize the area of the field? So what shape causes the area, or causes biggest area, maximal area? And I might as well say, and what is this area? I say what shape. I mean, the thing is, I've got to say subject to given field is a right-angled triangle, with the hypotenuse not equal to the... I don't want this to be the hypotenuse. So I'm not allowed to do this. I don't know, maybe it's not so crazy. Maybe one day he plans to build another fence over here. Who knows? So, that's the problem. So how do we tackle it? Well, step one, give some names to the variables. So we might as well mark them on here, but also write a sentence. So what are we going to need? Well, I don't know, there's two lengths of fences here. This is actually supposed to be an overhead view from a plane. But I'm still thinking of this as a triangle, so I'm going to give this length h, and I'll let this be capital H. I'll let this be B. So these are three lengths here. And then also, I'm going to let the area be A. So let's write this down. Let's be responsible here. Let H and B be the sides of the triangle, not hypotenuse, in feet. And let H be the hypotenuse in feet, as shown. And in my solution, I reproduce the picture. Why not? Just sketch it out on your thing, on your exam paper. Let A be the area in square feet. Okay? That's a good idea. Write all that down. Okay, so that's step one. Step two says, let's get a feel for the domain. Now, what's the extreme shapes? What are the extreme shapes that we could have? One possibility is that we let the triangle be something really thin like this. So this would be H and H. I mean, really, we could be even more extreme and put the fence right alongside it. But if we did that, that would be kind of silly. So the question is here, what are the actual values of little h and capital H? And in this case, they're both 150, right? We have 300 feet to play with. If these were actually the same, as in on top of each other, each of them would be half of the total length of fence, because we still got to go up and then back down. We can't just use all 300 going straight out. That's not a limiting case of this, as it were. So actually, we see that little h can be no more than 150. That's an endpoint there. Right? On the other hand, the other possibility is that we make little h almost nothing. And then big H would be like this. So, of course, H could conceivably be 0, in which case the fence just goes along the wall. These are both pretty dumb if you want to maximize the area. They actually have area 0 in both cases when you go down to the limit. So we're going to eliminate capital H, but it might be worth saying that it has to be at least 150 and no more than 300. See, in this case it is 150, but that's actually as short as it possibly can be. It's as short as it can be. Any other thing is actually going to be longer. Is that true? I'm not so sure about that. Maybe there's a shorter thing if we do it like this. I don't know. Anyway, the problem is not to maximize H. The problem is to maximize the area. So let's just concentrate on one of the variables, little h. We can easily work out its domain, and there we have it. Good. A is the variable we want to find the maximum of. So in step 3, we've got to write down some equations. Step 3. Write down some equations. Well, what do we know? We've got a whole bunch of equations. One thing we know is that the area, A, is equal to a half base height. Another thing we know is Pythagoras' theorem. B squared plus h squared is capital H squared. That's just Pythagoras. And finally, we know that little h plus big H is 300. The total length of fence is 300. So those are the 3 equations. No one is going to tell you what they are. You have to read the question and work out what they are. I'm going to leave the method up so that I can still refer to it from time to time. Right. So, there are the three equations on the board over there. Now we've got to eliminate. We want A equals something, and I've said we've got a good idea of what happens with little h, so let's eliminate little h. Okay, so the first thing we can do is say, well, capital H is equal to 300 minus little h. Now, if we take b squared plus h squared equals capital H squared, we'll use this value of capital H and write this as 300 minus little h all squared. Okay, this is good. We can actually make b the subject, solve for b here, and you get b squared is 300 minus h all squared minus h squared. And if you expand this out, it's a little bit messy. It's not too bad. You get 90,000 minus 600h plus h squared minus h squared. And the h squareds cancel out. That's kind of nice. So anyway, finally, b is equal to the square root of 90,000 minus 600h. And I'm actually going to pull out a factor of 100. See, 100 goes into this, 100 goes into this, and the square root of 100 is 10. So this is 10 root 900 minus 6h. That's cut it down to size a little bit. No problem. So I've solved for b. Finally, I have that the area is a half bh, which is 1/2 times this quantity times h, which I can simplify down to a is 5h root 900 minus 6h. Okay, so a little bit of algebra was required here, but ultimately we have reduced the situation to the case where we have the variable we want to maximize a, and it's just written in terms of one of the other variables, h, and we even know what that, or little h in this case, we even know what the domain is. In fact, let me come back over here and write 0 less than or equal to h less than or equal to 150. By the way, a comment about this. If h was bigger than 150, this square root, if you think about it, 6 times 150 is 900. So if h was bigger than 150, you'd be taking the square root of a negative number. That's clearly not reasonable. H actually could be less than or equal to 0, in which this would make sense, but it doesn't make much sense to have a negative length of fence. Then the fence would have to extend past the wall to the bottom of the figure, which I just erased, and that would be kind of silly. So, let me just erase this, and then we'll continue with the next step. So I've actually done step 4. That was step 4. I didn't write that down, sorry. But, next step is to differentiate. And we'll need the product rule. So let's just do it. Don't use the product rule on the 5. I'm going to write this up again so I can see it. 5h root 900 minus 6h. So if we use the product rule, dA dH. 5 is just a constant. So now I apply the product rule. It goes like this. Second term, v du dx. Well, du dx is just the derivative of h, which is 1, plus h times the derivative of the square root. Now the derivative of root x is 1 over 2 root x. So you're going to get 1 over twice the square root here. Then you have to multiply which just puts it up on the top, by the derivative. Okay, this has gotten a little messy here. I need to multiply by the derivative of 900 minus 6h, which is just minus 6. So there's the derivative. Let's simplify it a little bit. First observation, we can cancel out the 6 to a 3 and cancel out the 2. And then we can take a common denominator. Common denominator is just root 900 minus 6h. And that causes this to become 900 minus 6h. The square root goes away when you multiply through. And then I better subtract out another 3h. And that came from the minus here, then the 3, and then the h. And if you work this out, this is 5 outside of 900 minus 9h over root 900 minus 6h. And we might as well factor out a 9 and write this as 45 outside of 100 minus h over the square root. All right. That was a little bit messier, but we found the derivative. Question? No question. Sure? Okay. So there's the derivative. Now, where are the critical points? Part of this fifth step is to find the critical points. Well, it's quite clear that this equals 0 only when h equals 100. That's clear. The denominator is always positive or not defined. Could be 0, I guess, when h equals 150. So, but there you have it. There's the derivative. There's the critical point when h equals 100. And I propose to analyze this using the second method rather than the first, although you could do the first. Or if you felt like differentiating this again, you could use the second derivative, which is the third method. But let's just draw up a table of signs for the derivative. This is the easiest in this case. Here's h. Here's dA dH. The critical points at 100. We can see this. Plug in 100, you get 0. So that's flat. What if you put in something a little less than 100, like 99? Well, if you put in 99, the top is positive. It happens to be 45, but who cares? It's positive. The bottom's always positive because it's a square root. So up we go. 101, the top is negative, same as the other problem. So we clearly have a local maximum at 100 at h equals 100. But there's no other maxima, there's no other minima. Well, there's no other critical points. There might be minima. There's certainly no other maxima. So between, if this is the graph of the area versus h, all I know is that at 100, you have the one and only maximum. Now, you could check the endpoints if you want. Go back to the original formula here. We know the endpoints are h equals 0 and h equals 150. And that would allow us to tie this down to 0 and 0 here. But it's not even necessary. Once we're only trying to maximize in this problem. Once we've found the only maximum, and we've seen that it is a maximum, which is why this is really important to do this table, then we can confidently conclude only max, so it's the global max as well, the absolute maximum, i.e. maximum area occurs when h equals 100. h equals 100. So that's step 6. So I'll stop writing down the steps. You can put them in. Okay, we've almost finished the problem. To finish the problem, we ought to say what the dimensions are, because the question was what shape is the triangle, what are the dimensions of the triangle, and what is its area. So you have to go back to your original equations, which I've even erased now, although you can sort of see them all over here. So we go back to that, and we have capital H is 300 minus little h, which is 300 minus 100. It turns out to be 200. And we have b squared plus h squared equals capital H squared. So this means b squared plus 100 squared is 200 squared. Don't let the hundreds worry you too much. This just means, think of this as b plus 1 equals 4. So b actually works out to be root 300. And so the area is a half BH, which is a half. Root 300 is 10 root 3, of course. So it's a half times 10 root 3 times h, which was 100. Oh, I wrote 1,000. Said 100. So we just substitute in all of these things, and we end up with 500 root 3. Are we done? More or less. Let's just write it up in a summary. The maximum area is 500 root 3 square feet when the triangle has height 100 feet, base 10 root 3 feet, hypotenuse 200 feet. Done. Question? Okay, in the area equation here, this one here. Yes, it's very possible. What did I do wrong here? What did I do wrong? Oh, I know what I did wrong. B is wrong. Thank you for pointing this out. That's actually another way of finding, of course, the area. I was a little bit sloppy with this. I should have done this more carefully. B is actually root 300,000, if you work it out. It's 4... let's start again. B squared plus 100 squared equals 200 squared. 200 squared is 40,000. 100 squared is 10,000. So B squared is 30,000, not 300 as I said. My apologies. And so that is 100 root 3. So you see, I wanted to write that extra 0 there. I really should have written it here. And so this works out, the area works out to be 5,000 root 3. And let's go back over here and change this.
Is that the same thing as 500 root 300?
Yes, so now let's look at that. Root 300 is root 3 times 100, which is 10 root 3. So yes, this time there. But I did make a mistake. Thank you for pointing that out. I frequently make mistakes, and if you see them, please point them out. And if you are watching and it's too late to point it out, just email me and give me some, tell me. I'll try to be more careful. Yes, I'm just looking at my notes here, and the answer is indeed 5,000 root 3, according to my book. So should have checked it. Anyway, good. So there's the reality check, right? You write down the answer, then you go back and you just scan this and say, oh, wait, it's 500 root 300. Right? When h is 100, you get 500 root 300. So I got it wrong. So excellent double checking. Any other questions about this example now that it is hopefully correct? You see why I didn't want to take the second derivative, by the way, use that method. It's a real pain. Even taking one derivative was a pain. But we had no choice. All right, let's look at one more example. Then we can go on to L'Hopital's rule, unless there are any other questions. This one is a little bit more involved. It's got a couple of parts, and I want to show you another potential method for solving it. But here's the question. This is a bit of a classic in some way, although I'm going to have a little twist on it. We're going to make cans storing soup or whatever. And they're going to be closed. So it's a cylinder with a top and a bottom. Sometimes the problems involve no top, or sometimes not even a top or a bottom. But here I want to have both the top and the bottom. And I want the volume to be 16 pi cubic inches. That's the volume of my can. That's how much soup I want to have. Now, of course, you rarely see a can of soup that says volume is 16 pi cubic inches. But, you know, pi is about 3, so this is around 50 cubic inches. So I could imagine seeing that. It would probably be in ounces, but whatever. Let's not get too bogged down. This is a nice, convenient value, and we won't have to use a calculator. Right, so I'm going to tell you that this can costs 2 cents. I'm going to put a slash through the C, because otherwise we'll think of it as the letter C. So I'm going to say the can costs 2 cents per square inch of metal. So what are the dimensions of the cheapest can? And how much does it cost? What are dimensions and cost? Well, dimensions and cost of the cheapest can. That's a fairly standard question. Here's something that makes it a little bit different. Suppose now that in addition to the metal and the base fee, I guess, of actually curving the metal, you have to pay someone to weld the top shut and the bottom shut. You actually want to have them, you know, welded shut. So if it also costs 14 cents per inch, not per square inch, per inch of welding for the top and bottom, how does the, what now, redo A. Redo A. What now are the dimensions and the cost of the cheapest can? So you'd sort of think, well, there's the cheapest can, but if I also have to pay someone to weld it, it probably is better to make it a little skinnier, longer and skinnier, because then there's less welding. That's going to cost some money as well. Okay, is the question clear? Does anyone have any questions about the question, as it were? All right. Well, so luckily there aren't too many variables in this case. Just 3. Let's redraw the cylinder. R, H, and V is going to be its volume. So let R be the radius and H be the height of the cylinder, of the can, and they're both in inches. And let V be the volume. Well, it'd be one, I said there are only 3 variables, but I think I spoke a little bit too soon. In inches cubed, well, in cubic inches. I spoke a little bit too soon because the volume is actually 16 pi, so we don't really need that. It's not really a variable, but what the hell, we'll just give it a name V, which we'll then throw away. But what else do we actually need? We need the cost. But what does the cost depend on? It's 2 cents times what? The surface area. So we're also going to need A. So we don't really need the volume. We're going to need A. So let A be the surface area in square inches. And let capital C be the cost in cents. So everything has a unit, even the cost. And this is the one that we want to minimize. All right, well, let's write down some equations. The volume is pi r squared h, which happens to be equal to 16 pi. So we already have an equation, r squared h is 16. There's a first equation. Now, what about the surface area? You need to know what the surface area of a cylinder is. It's not given in the problem. It may not be given to you in the statement. You just have to know it. So what happens is, if you think about, forget the top and the bottom, again, this is actually a rectangle. If you cut it down along here and unfold it, it's a rectangle of 2 pi r by h. So you get 2 pi r h, plus the top and bottom are both circles of radius r. So the top has area pi r squared, the bottom has area pi r squared, so actually together it's 2 pi r squared, top and bottom. By the way, imagine you took a roll of toilet paper after it's finished, you know, just a little cardboard thing, just like this, and you chop it up and unfold it. Which dimension do you think is longer, the circumference or the height of the toilet paper roll? I don't know. Have you tried it? Who thinks that the height is longer than the circumference of the toilet paper roll? You know what they look like. Who thinks that the circumference is longer than the height? Yes, actually, it's true. The circumference is about an inch longer than the height for a standard roll of toilet paper. It's sort of surprising, isn't it? Well, 2 pi is actually bigger than 6. So the radius has to be less than 1/6 of the height for the circumference to be small. Anyway, that is a complete tangent, and I don't even want to get into toilet humor. So let us just go back to this A here and ask yourself, what is the cost? Well, that's the area in square inches. The cost is 2 cents times this. So since we're working in cents, the cost is just 2A, which is equal to 4 pi r. I'm going to take out a factor of, so it's 4 pi r squared. There's a factor of h and a factor of r. So the cost is 4 pi r times h plus r. Now we can eliminate either r or h, but it seems like it's easier to eliminate h because there's only one of them and there's 2 r's there. So I'm going to take here h equals 16 over r squared. I'm going to use those two equations, and once I get some board space, I will simply just write down an equation for the cost c in terms of the radius r. And once we know the radius, we'll know everything about the can. All right. So what do we got? We have cost is 4 pi r outside of h, which is 16 over r squared, plus r itself, which we can write down as, it might be easier to differentiate if we just write it as 4 pi outside of 16 over r plus r squared. It'll be easier to differentiate like this because in this formulation, you sort of got to use the product rule, but there's no need to if you expand it out. Okay, so we've finished up to step, step 3, step 4. We've eliminated all the variables. Here's the thing we want to minimize in terms of one variable. So let's differentiate as according to step 5. We have dc dr. 4 pi is just a constant. The derivative of 1 over x is minus 1 over x squared. So in terms of variable r, minus 1 over r squared times the coefficient 16. And then you have plus 2r. And this equals 0 when minus 16 over r squared plus 2r equals 0. Or if you multiply through by r squared, you will get 2r cubed equals 16, r cubed equals 8, and the only solution is r equals 2. By the way, I kind of skipped over step 2. I should probably do that. I should probably come back to that now before it's too late and ask, what are the extremes here? Well, one extreme is that the radius could be tiny, but in order to get our volume, we'd need like a ridiculously tall can. I couldn't even fit this in the book because the page was too short. So, but that's pretty much it. If R is really, really tiny, in order to get your volume of soup, you have to go through the roof. So this R could be as small as you like. On the other hand, R could also be humongous. You could have this huge radius, but you then need a tiny height. The volume to get the volume you want. Now, this is ridiculous. I mean, you're using a huge amount of metal here. This is also ridiculous, though, as it turns out. The height has to be so big that what's going to happen is, even though it's very thin, it's just going to be quite a lot of metal still. And you can actually see that if you look at the cost function. What happens when R goes to 0? This term blows up. The costs go through the roof, as does the can. But if R is big, this term's not a big deal, but that term becomes huge. So neither of those can be right. Everything has to be somewhere in the middle. And here we have found that at R equals 2, we have a critical point. It's the only critical point. Is it a maximum or is it a minimum? Let's use the second derivative to find out. It's quite easy to find. We just differentiate this. If you think of this as the first term, here's my rough work, minus 16R to the minus 2. So if I differentiate that, I get 32R to the minus 3. Right? You multiply by minus 2, you get 32, and knock it down by 1. And the other one is just 2. So this is the second derivative. And actually, this term's always positive when R is positive. You know, I didn't summarize what the domain is, but R can be any positive number. That's what I was trying to say before. This, of course, is positive. So this is greater than 0 when R equals 2, or any R, or any number greater than 0. So the second derivative is positive, which means that the curve looks something like this. Has an asymptote there, it just goes off to infinity. I don't know how high this is, but 2 is the only minimum, so it must be the global minimum. So R equals 2 is an absolute minimum for C. And that is the answer to the first part, provided that we summarize it. We know that H is 16 over R squared, which is 16 over 4. Is 4, and the cost is equal to 4 pi R 16 over R squared plus R. That's our original formula. So it's 4 pi times 2, 16 over 2 squared plus 2. So this is 16 over 4 is 4, plus 2 is 6. 6 times 2 is 12. 12 times 4 is 48. And we get 48 pi. So for part A, the the minimum cost is 48 pi cents, and it is achieved when the radius is 2 inches and height is 4 inches. So the radius is 2, that means the diameter is 4. And the dimensions of this can has the same height as diameter. Of course, 16 pi is the volume. That doesn't really matter. The cost of 2 cents doesn't really matter. If you have any closed can whatsoever, a fixed volume, it doesn't matter what the volume is. And it doesn't matter what the cost is. The cheapest closed can of a fixed volume has the height equal to the diameter. Of course, what that height and diameter actually are depends on what the volume is. And what the cost is also depends on the volume. But if you think about it, the numbers weren't really specific. It's more the shape of the thing. Pi r squared h. Interesting sort of stuff. Okay, we have to do part B. The cost is the same as it was before, plus the welding. the welding involves 14 cents per inch. And where is the welding? Well, if you look back over here, top, bottom. What is this length? It's the circumference, 2 pi r. Another circumference, 2 pi r. So for part B, welding adds 14 cents times 2 for the top and the bottom of circumference each time. 14 times 4 pi r. I'm just going to leave this as 14 times 4 pi r. So the new function of c, now c is equal to the old one, 4 pi r, 16 over r squared plus r, plus an extra 4 pi r times 14, which I can just factor. Well, let's do it over here. It's just 16 over r squared plus r plus 14. Or if we expand this out, we get 4 pi 16 over r plus r squared plus 14r. Okay, so I don't propose to redo the whole problem. R is still between 0 and infinity, and the cost still blows up at those extremes, but now we just have this extra term. So let's just differentiate this. It's almost the same as the previous one. This is minus 16 over r squared plus 2r, but now we have this extra 14. So this is going to change things a little bit, not too much. So this equals 0 when minus 16 over r squared plus 2r plus 14 equals 0. And I'm going to come over here and solve this. So multiply through by r squared and divide by 2 while we're at it. And you get r cubed plus 7r squared minus 8 equals 0. So it's similar to what we had before. We just had r cubed minus 8 equals 0. Now we have a 7r squared in there as well. So unfortunately, this is a cubic. And to solve the cubic is not so easy. There is a cubic formula, but it's horrible and you don't know it, probably. So instead, our technique is guess a root. Try to guess a root. Can anyone see a value of r that makes that work? 1. Yeah, try 1 and minus 1. Those are always the first ones to try. Failing that, try other factors of this number. So factors of 8. If 1 and minus 1 didn't work, I'd just try 2, minus 2, 4 and minus 4, possibly 8 and minus 8. Anyway, r equals 1 is clearly a solution. But is that the only solution? Are there any others? The only way you can be sure is to realize that we must have a factor. Yes, you have to set up a division. You must have a factor of r minus 1. And if we try this, we get r squared, r cubed minus r squared, and we have 8r squared minus 8. So that is going to be what? Plus 8r. And if we multiply this, we get 8r squared minus 8r. And you get 8r minus 8. So plus 8. R squared plus 8r minus 8. So actually, any factor of this will also work. Well, what are the factors of that? I have run out of room, so I must continue. Step 7 of the summary finally bit the dust, because I forgot about it. Didn't quite fit it onto the above board. What you going to do? Let's move on. We've got more to do. Okay, so we've ended up with or r squared plus 8r plus 8 equals 0. The solutions to that would be r equals minus 8 plus or minus the square root of b squared minus 4ac. That's 64 minus 32 all over 2a. Now, these are legitimate possible critical points, but what is root 32 approximately? Who can tell me what it's between, at least? Yeah, root 32 is between root 25, which is 5, and root 36, which is 6. So you should think of this as between 5 and 6. And so, regardless of whether you add it on or subtract it from minus 8, if you add it to 8, you get minus 2 at the worst. And obviously, if you subtract it, it's even more negative. So both these solutions are negative. And so they would be critical points if we could have a negative radius, right? Which is sort of weird. If you had a negative radius, well, all the r squareds would sort of make sense, but the interpretation would be that the welding is actually negative cost. You found some person to somehow weld for, not only for free, but they pay you for the privilege of welding. That's sort of what happens. So this is all very insane stuff. So we ignore them. Ignore these cases. R equals 1 is the only critical point in the acceptable domain from 0 to infinity. Okay, let's again check that it's a minimum. We have dc dr, which was in the other board here. I'm just going to differentiate. Actually, I'll write it out again. What the hey? What do we get? 4 pi minus 16 over r squared plus 2r plus 14. Actually, the second derivative in this case is the same as it was in the previous case. It's 32 over r cubed plus 2. This is a constant, so its derivative is again 0, and this is again positive, so once again we have a local minimum, etc. And I'm going to leave the concluding sentence to you. The concluding sentence has got to involve the fact that r equals 1, h will be equal to 16 over r squared, once again, which is 16, and the cost is equal to whatever it is. You can find it in the book, but instead I'm going to leave the rest as an exercise for you. All right? Any questions about that part or that example? I got to clear some board space, so if you do have a question, you can start shouting it out. Before we move on to L'Hopital's rule, I want to show you a slightly different technique for solving the first part of the problem. It is an official technique, and sometimes it is the only way to solve these sorts of problems. But in this case, it's not. But it is actually kind of neat. So let's just go back for a second to our original equations. We had r squared h equals 16. And we also had that the cost is equal to 4 pi r outside of h plus r. Or if you like, 4 pi, let me just rewrite it as 4 pi rh plus r squared. Okay. So what do we do? What we did was eliminate h, and that was fine. But, and that was according to the method, but there is an alternative way. We can actually use implicit differentiation. Instead of eliminating r, we could just differentiate both of these with respect to r implicitly. So let's try an alternative method, which is to differentiate both with respect to the variable r, which is the one we wanted to make the only variable. If instead we do ddr of both of these, what do we get? Well, if you differentiate this implicitly, you get h times the derivative of r squared, which is 2r, plus r squared times the derivative of h, but with respect to r, equals the derivative of 16, which is 0. So you can actually rearrange this and see that dh dr is equal to minus 2rh over r squared, which is actually minus 2h over r. That's a valid equation for dh dr. Now, what if we come over to the cost here? dc dr is 4 pi, and we have to differentiate this implicitly. Again, it's h dr dr, which is just h, plus r dh dr. And then this other term, the derivative is just 2r. And now we can, instead of eliminating h from the original equations, we didn't do that, we differentiated instead. The next thing is to eliminate dh dr. Maybe that's easier. If we do this, we get 4 pi h plus r, and dh dr is minus 2h over r plus 2r. And if you work this out, the r's cancel, and you get h minus 2h. So you get 4 pi 2r minus h. And that is another way of looking at the derivative, dc dr. It's just it hasn't eliminated h anymore. It's 4 pi 2r minus h. And this equals 0 when h equals 2r. So we have our critical point. We don't know what r or h is. R. We don't know what either of them are. But we know that the critical point occurs when the height is twice the radius, i.e. the height's the same as the diameter. So it's a sort of interesting roundabout way. The problem is, how do we know it's a minimum? Well, let's go from here and take d2c dr squared. We have to differentiate this with respect to r. We get 4 pi 2 minus dh dr. Of course, we know what dh dr is. It's minus 2h over r. So you get 2 plus 2h over r. And the only thing we care about is that this is always positive. So again, the curve is concave up, and this is a minimum. This is now a minimum. It's really weird, you know, it's all implicit stuff here. But look how simple the computation is. Simpler than the other one. So this is now a minimum. And of course, to find out what it is, you have to go back into the original equation, r squared h equals 16. We know h equals 2r. So this means 2r cubed is 16. R equals 2 as before. And we immediately know h equals twice that much. And you continue as before. And you can actually do the second part of the problem involving the welding using this method as well, without too much difficulty. So you see, this method, it's a little easier, maybe in this case, although it's trickier because you've got all the variables floating around. However, you look at this, it's quite easy to solve for h, right? R squared h equals 16. But what if it was more complicated? What if it was like r squared h plus hr cubed plus sine h plus cosine r, some mess that you couldn't do? Well, then this would be the method. This would be the method. Because you can eliminate, actually, dh dr. When you implicitly differentiate, you find that you just get very simple function of the derivative. So it's easier to eliminate the derivatives. So, I don't know. I'm just showing you this. I haven't seen a lot of problems where you have to do this implicit method. But the point is that instead of eliminating all the variables, you can actually just differentiate implicitly with respect to one of them and then eliminate the derivatives. And that may be the best way of solving a problem. All right. Well, as I say, there's one more example of optimization in the book, but I'm not going to go through it. It's a little bit harder. You're welcome to look at it. Are there any other questions about optimization apart from help me solve this problem, which I'll do at 9:30? So I go on to L'Hopital? All right. I don't think I'm going to get much done on integration. That's okay. Next week. I'll keep it all in one go. We'll see. Maybe I can do L'Hopitals pretty quickly. Okay. Here is a random little topic. L'Hopital's rule. We could have done it a lot earlier. I don't know. Here it is. Doesn't really have much to do with optimization. What it is it's a new technique for finding certain limits. We've looked at plenty of techniques for limits. We looked at poly over poly, things with square roots. We looked at exponentials, trig limits. Here's a different technique. And in its purest form, which I'm going to call type A, I'm going to identify certain different types. These are my names, by the way. I haven't seen another book. I just call it type A because I want to call it something. So the classic sort of thing is you have a limit that looks like this. Limit x goes to A, f of x over g of x. A lot of the time, you have limits in these ratios. In fact, every derivative is a ratio. Remember, f of x plus h minus f of x over h, that's as x goes to 0, that's a ratio. And a lot of the time when you substitute in A, you get, so you try to plug in, you get f of A over g of A. A lot of the time, this is equal to 0 over 0. That is an indeterminate form. If you actually substitute that in and you get 0 over 0, that's an indeterminate form. And we've seen you have to do something clever. Factor, multiply by a conjugate, who knows? Multiply and divide, all sorts of different techniques we looked at. Here is another technique. If you have this, then this is what L'Hopital's rule says. It says that if instead of the original f over g, you can just differentiate the top and the bottom separately. No quotient rule here. This is not quotient rule. It looks like a quotient, but it has nothing to do with the quotient rule. You're just differentiating the top and the bottom separately. If you can do this limit, you can do this limit. Pretty nice rule. Okay, what I'm going to do is just show you one or two simple examples of it, and then I want you to leave a little bit of space because I have to elaborate on this rule. But first of all, here's a really simple problem. Limit as x goes to 3, x squared minus 9 over x minus 3. Okay, we did this before, or something similar to it, by factoring the top and bottom, and then you cancel out a factor of x minus 3 and substitute. You can try doing that. You should get the answer 6. Should only take a few seconds. But let's just use L'Hopital's rule. See, if we plug in 3, we get 9 minus 9, which is 0, over 3 minus 3 is 0. So we do have this form, indeterminate form, 0 over 0. So I like to say this equals using L'Hopital's rule, and I'll put above the equals a little L apostrophe H to pretty clearly indicate that we're using L'Hopital's rule at this particular step. And you get the limit as x goes to 3. We just differentiate x squared minus 9. You get 2x. And you differentiate x minus 3, and you get 1. And in this particular case, no problem. Now we plug in 3, you get 6 over 1, which is 6. That's a pretty boring example. Here's one that we could not have done earlier, where the rule is pretty indispensable. We didn't really have a technique for doing this. If you do x minus sine x all over x cubed, classic limit that. Here's the deal. We have been saying that sine of a small number behaves like the small number itself, right? Sine x over x goes to 1. But that doesn't tell you about x minus sine x. If you make the mistake of saying, oh, this is just like x, right? So the top is like 0. Can't do it. This like thing, as in, you know, this behaves like this, that only works for products and quotients. It does not work for difference. So instead, we plug in 0. We get 0 minus sine 0 is 0. And 0 cubed is 0. So it's an indeterminate form. It's important that you write this down somewhere. That's part of the solution. It's not just the rough work. It's an observation that, hey, I plugged it in and I got this 0 over 0 form, so I'm allowed to use L'Hopital's rule. So this is equal to the limit as x goes to 0. We simply differentiate x minus sine x to get 1 minus cosine x all over x cubed, which is the derivative of x cubed is 3x squared. I'm going to leave this space for some comments. Okay, so this limit equals this limit. We still have to solve this new limit, of course. Now, if I plug in 0 once again, I get 1 minus cosine of 0 is 1. Guess what? That's 0, and the denominator is 0 again. So once again, I can use L'Hopital's rule. I'm going to use it twice in this problem. And I get the limit as x goes to 0. Derivative of 1 is nothing. The derivative of cosine is minus sine. So actually, we have minus sine x, so that's just sine x. And on the bottom, the derivative of 3x squared is 6x. Now, actually, you could use L'Hopital's rule once again if you like. It's a 0 over 0 again, and you could just differentiate it, and you'll get the right answer. But we already know that the limit of sine x over x is 1. So with the factor of 6 there, we get 1/6. So that's the value of that limit. Never would have guessed it. X minus sine x over x cubed, 1/6. Where on earth does that come from? It's not obvious at all. Actually, if you think about it, where it really comes from is you differentiate x cubed to get 3x squared. You differentiate that to get 6x. That's where the 6 is. It's 3 times 2. But I will not go into that further until we look at Taylor series, which is not till Math 104 as far as you guys are concerned. So never mind about that. What I want to do is come back to this statement of L'Hopital's rule and elaborate on it a little bit. The first point is that you need a 0 over 0 form. Although in a few minutes I will show you an example where another possibility which also works is you can have infinity over infinity. Sometimes you get that indeterminate form, and in that case you can still do it. And you're allowed to have a minus infinity, of course, so I'll put plus or minus infinity. Doesn't matter if it's minus infinity over infinity. Okay? Otherwise, you cannot use this L'Hopital's rule. So you need to plug it in and establish that you have one of those. Now, that's one comment. 2, it only works if the right-hand limit or the right-hand side exists. So it's conceivable that you say, oh, I'm going to use L'Hopital's rule. This equals this. It's conceivable that the new limit that you find does not exist. It's unlikely, but it's possible. Well, that does not mean that the original limit does not exist. It just means L'Hopital's rule didn't really work. There's another technical condition as well. Actually, you need g prime of x not equal to 0 near x equals a. That is such a technical condition that I've seen textbooks that omit it. The only way that can really screw up is if the derivative is like one of these sine 1 over x things that keeps going back to 0. So, you know, you don't need to check that. I just feel like I should state it. Okay? However, something that is relevant and kind of nice is it also works for one-sided limits. And it even works at infinity. As long as, of course, you replace both of these by the same thing. So these could both be right-hand limits, left-hand limits. They could both be limits at infinity or minus infinity. Okay, so I'm going to show you a couple of examples, a couple more examples. And then I'm going to show you a few other variations, types of problems that lead to L'Hopital's rule. There's only one L'Hopital's rule. The other types actually reduce to the original. But that's all there is to this whole thing. All right, let's see what other examples I have up my sleeve. There's more in the book. This is all in chapter 14, of course. Let's take a look at this limit. Limit as x goes to 0 from above, cosecant x over 1 minus log x. All right. First thing first, substitute in x equals 0, or at least 0 plus. Well, 0. Let's plug in 0. What's cosecant of 0? Cosecant is 1 over sine. What's sine of 0? Yeah, sine of 0 is 0, so cosecant of 0, it's not that it so much doesn't exist. We're only doing a right-hand limit. So 1 over 0, or 1 over a tiny positive number, is a huge positive number. So if I actually plug in 0 plus into this, you should think of this as being infinity. How about log of 0? What's log of 0, or at least 0 plus? What happens to log as x goes to 0? Negative infinity. Okay? If you ever had to remember one useful pseudo-equation, which is not a real equation, it's that log of 0 is minus infinity. Of course, it doesn't exist. What really works is that the limit as x goes to 0 from above of log x is minus infinity. But you might as well just learn that when you plug in 0, you get log of 0, that's minus infinity. So, of course, when you take the negative of it, it's plus infinity. So, actually, this is the indeterminate form infinity over infinity. And if you then are able to, well, then you are able to use L'Hopital's rule. So if you do, you just have to differentiate the top and the bottom. What do we get? Well, cosecant, the derivative of that is negative cosecant x cotangent x. And the derivative of 1 is nothing. The derivative of minus log x is minus 1 over x. So if we sort of simplify this a little bit, we get x cosecant x cotangent x. And if we simplify this, I kind of want to write this like as follows. X over sine x times 1 over tan x. What happens to x over sine x as x goes to 0? Well, what happens to sine x over x? Sine x over x goes to 1. So does its reciprocal. So this goes to 1. Tan x, of course, goes to 0 from above, so 1 over it. So this goes to 0. So unfortunately, the whole thing goes to infinity. 1 over 0. Can't work. That's the one-sided limit. The two-sided limit wouldn't exist. Wouldn't exist partly because the left-hand limit here would actually be minus infinity, but really the reason it wouldn't exist is because you can't even take a log of a negative number. Okay, so here's another example. Suppose we take the limit as x goes to infinity of x cubed over e to the x. Can anyone tell me what this is, just without doing any work? Just what is this? We've seen it before. What's that limit and why? It's 0. Why? Yeah, exponentials grow faster than polynomials. You could replace the top with x to the billion, which grows really, really fast. Overshoots e to the x at the beginning, but e to the x catches up and overtakes it, passes it, and leaves it for dead. It's so far ahead when x is large enough that it's not even funny. The ratio of this, it's huge to absolutely freaking enormous. That ratio is 0. But we can prove it. Look, if you plug in infinity, of course, you get a huge number cubed is a huge number. E to the huge number is a huge number. So this is infinity, infinity. We can use L'Hopital's rule, and we get 3x squared on the top. But the bottom is still e to the x. And of course, it's, again, infinity over infinity. So we again use L'Hopital's rule. And you now get 6x on the top and e to the x on the bottom. Once again, infinity over infinity. So we'll use L'Hopital's rule for the last time, promise. And you get 6 over e to the x. Now you cannot use L'Hopital's rule because it is 6 over infinity. But of course, if you have 6 over a huge number, that limit is 0. So clearly this is going to work for any power of x, even x to the billion. You just have to use L'Hopital's rule a billion times. You do it by induction, of course, so you don't actually have to sit down and there and write equals LH a billion times. But nevertheless, you see the pattern, right? Every time you Differentiate, the top weakens slightly by 1 degree, but the bottom just stays the way it is. It's impervious. It resists. So e to the x grows pretty quickly. If you think about it, it sort of makes sense, right? When x is large, e to the x is large, right? But the derivative is also e to the x. That means the slope is large. So it's large and its slope is large, which means that it's just getting large really quickly. Whereas polynomials, the slope eventually, the slope of the slope of the slope eventually is a constant number. So they can't keep up, cannot compete. Okay, so actually I don't claim that that's a formal proof of any power, but you can see how the pattern goes. Now one more example before I look at the other types. What is my example? Limit x goes to infinity. No, it's not infinity, it's 0. X squared over cosine x. Okay, let's use L'Hopital's rule. You get limit as x goes to 0. Derivative on the top is 2x, and the derivative on the bottom is minus sine x. And actually, I can pull out the minus 2, and I get the limit as x goes to 0 of x over sine x. This is just the reciprocal of the sine x over x, and you get minus 2. Okay, does that make any sense? You've got a question. You don't like it. A lot of you don't like it. Okay, I know I told you to say when I was making a mistake. This time I actually knew I was making a mistake. See, even if I didn't, let's do a reality check here. When x is near 0, x squared is positive, cosine x is positive. How can the limit be minus 2? How can the limit of something that's positive be minus 2? Okay, clearly this is just all bogus. No. Well, that's fine. I can't use L'Hopital's rule because if I plug in 0, I get 0 over 1. It's not an indeterminate form. In fact, the answer is just 1. It's just 0. It's just 0 over 1. Okay, I corrected myself before I had a chance. Talking for 2 hours, you're bound to say some really stupid stipulations. Okay, so anyway, don't use L'Hopital's rule unless it's an indeterminate form. Okay, but I'm glad you all caught me out on it. Right, so let's look at some other types. Here's a type I'm going to call B1. There's B1 and B2. And that is because they're both reduced to A, hopefully. B1 I'm going to consider as infinity minus infinity. Sometimes you plug in and you get infinity minus infinity. So A, I didn't actually write this down, but A was 0 over 0, or plus or minus infinity over plus or minus infinity. And we used standard L'Hopital's rule. B is sometimes you get infinity minus infinity. Now here's an example of such a thing. Limit as x goes to 0, 1 over x minus 1 over sine x. And actually it would be more accurate if I put a plus or minus outside there. Let's do that. Okay, so this is actually quite a famous limit in some sense. I've seen it all the time on Math 103 exams and quizzes. The interesting thing is when x is positive but close to 0, this is huge and this is huge. Whereas when x is negative, this is a huge negative number, and that's a huge negative number. So that's why I put plus or minus. It's either infinity minus infinity or minus infinity minus minus infinity. Anyway, whatever. It's not a fraction, so we can't use L'Hopital's rule directly. However, it's a difference of fractions, so we can take a common denominator of x sine x and write this as sine x minus x. And now it is a 0 over 0, as you can see by plugging in. So we are perfectly justified in using L'Hopital's rule. And you get cosine x minus 1 all over, and we have to use a product rule on the bottom. You get v du dx is 1 plus u dv dx is x cosine x. Now again, this is a 0 over 0 case because cosine of 0 is 1 minus 1 is 0 on the top. That's 0, that's 0. So it is 0 over 0. So I use L'Hopital's rule once more, and I get the limit as x goes to 0. Derivative of cosine x is minus sine x. On the bottom, the derivative of sine x is cosine x. Better use the product rule again. You get cosine x times the derivative of x plus x times the derivative of cosine x, which is actually minus x sine x. So there's the derivative, and if you now plug in 0, you get 0 over 2. Because cosine of 0 is 1 plus 1 minus 0. So the answer is just 0. Okay, so moral of the story, if you have a difference of two fractions, take the difference. Okay, that's all very well if there are two fractions. What if there aren't? Any questions about that example while I'm erasing this, by the way? If you have one, you know the drill. All right. Well, here's another example. In fact, let me make sure I get it right. Limit as x goes to infinity, square root x plus natural log of x minus the square root of x. Nasty example. So the deal here is, it's not a fraction. It's not even the difference of two fractions. So it's not so easy to write it as a over b. But you can do it if you recognize that it just has to be multiplied by a conjugate expression. So let's write it out again and multiply it by the conjugate expression. X plus log x square root plus square root of x over itself. And if you multiply out the top, it's a difference of squares. It's that squared minus that squared, which is just x plus log x minus x. So the x's actually cancel out, and if you do it, you find you get the limit as x goes to infinity of just log x on the top over square root x plus log x plus the square root of x. Not so bad, huh? Now it's a fraction. In fact, if you put in x equals infinity, log of infinity is still infinity. Bottom is the square root of infinity plus infinity. Of course, there's no such number as infinity. What I really mean is if you put in a huge, huge number, this is huge, and it just gets huger and huger. So in any case, you do get infinity over infinity. So you justify it in using regular old L'Hopital's type A, which is just L'Hopital's rule as a fraction. And the derivative of log x is 1 over x. Unfortunately, this thing's a bit of a mess to differentiate. The derivative of a square root is 1 over 2 times the square root. But you need to multiply by the derivative, which is 1 plus 1 over x. And in this case, the derivative is just 1 over 2 square root of x. Okay, so this is a bit nasty. Rather than simplify it, just ask yourself what happens as x goes to infinity. Well, actually, I will simplify it a little bit. Forget what I just said. I'm going to multiply top and bottom through by x. So the top just becomes 1. And then we multiply this by x, and you get x plus 1 over 2x plus log x, quantity square root. And the other term is root x over 2. Okay, that's better. That's better. Now ask yourself, what happens on the bottom? X goes to infinity. This term here goes to infinity. It becomes really large. And this term, well, in the book I look at it separately, but actually you don't even need to look at it separately. See, if that goes to infinity, this quantity is positive, so it just makes the denominator even larger. So this goes to infinity already, so automatically, as I say, if this were negative, things would be different. But because it's positive, this also goes to infinity, and you get 1 over something very large, which is 0. Kind of a clever trick there at the end. If you don't believe it, use L'Hopital's rule again on this infinity over infinity case. It's a good exercise. Use that in order to find that limit. It's also infinity, as it turns out. After all, the top behaves like x, and the bottom only behaves like root x. So the overall limit is 0. Okay, so in type B1, which is a difference of two large quantities, maybe negative large, but it's the difference between two large quantities, hopefully you can either do a common denominator or you can do some conjugate trick, but you cannot always solve them. There are examples of type B1 that you cannot get into a fraction no matter how hard you try. So that's what I have to say about B1. Any questions about that? Well, let's quickly talk about B2 then. It's beginning to sound like vitamins. B2. That type is going to be 0 times infinity or minus infinity. Now, here's an example. Classic example. Last week we drew the graph of x log x, and we saw that it doesn't actually have any vertical asymptote at 0, but I kind of just said the limit is 0, never really proved it. Now we can really do it. Now we can really do it. Unfortunately, it's not a product. I mean, it is a product. It's not a quotient. But products turn into quotients quite easily. What you do is you pick one of them, throw it on the denominator as the reciprocal of itself. See, x can go down the bottom as 1 over x. Kind of a neat little trick. Now, if you actually look at this, log of 0, remember, is minus infinity, at least in form. 1 over positive 0 is plus infinity, so you get the indeterminate form minus infinity over infinity. That's cool. We can use L'Hopital's rule. You simply differentiate the top and the bottom. Log x has derivative 1 over x, whereas 1 over x itself has derivative minus 1 over x squared. If you unravel this, you get limit. Just multiply the top and bottom by x squared, and you simply get minus x. Plug in x equals 0, and you get 0. So that limit I call B2. Again, like all the other B1 cases, both of those, it reduces to a type A case. So you can use L'Hopital. Here's another example. Limit as x goes to pi over 2. X minus pi over 2, tan x. Is that exactly how I have it? It is how I have it. Oh, actually, before I do this, I just want to go back up here for 1 second. Forgot to say something. I could have picked log x on the bottom. So instead, I would have had the fraction x over 1 over log x. That's true. It is a fraction. That puts it into 0 over 0 form, if you think about it, which is fine too. Problem is it doesn't work. You can try it if you like. The top is just 1, but the bottom will give you such a mess. You differentiate it, and all of a sudden you'll find that you get an even worse limit out of it. So the problem is that 1 over log x is not a very nice thing to differentiate. You have to use the quotient rule. Chain rule will work. Whereas 1 over x is a nice thing to differentiate. Avoid putting logs on the bottom. If that's one of your terms, try the other term. On the other hand, here, actually tan is a nice thing to put on the bottom. Let's first see why we have to do this. If I plug in pi over 2, undoubtedly I get a 0 there. What about tan pi over 2? What's that? What's tan of 90 degrees? Anyone? Nope, tan pi over 4 is 1. What's tan pi over 2? Remember the graph of it? It isn't defined. You're quite right. It has a vertical asymptote at pi over 2. So it's not even infinite. It's infinite plus infinity on the left side and minus infinity on the right side. In any case, it is plus or minus infinity. So it turns out the best one to pick is the reciprocal of tan because, again, my general principle is if it's nice to differentiate, when you take the reciprocal of it is probably the right thing to do. In this case, if you put it on the bottom, 1 over tan is cotangent. We know that's quite easy to differentiate, and we know what the derivative is in any case. So now we've turned it into a 0 over 0 form. After all, if tan pi over 2 is plus or minus infinity, depending on which side you go to, the reciprocal must be 0. Indeed, cotangent of 0 is just 0. After all, it's cotangent of pi over 2 is 0. It's cosine pi over 2 over sine pi over 2, which is 0 over 1. So this is a 0 over 0. We can use L'Hopital's rule, fully justified in doing so. And we just differentiate. We get 1 over the derivative of cotangent is minus cosecant squared. And of course, sine pi over 2 is 1. So cosecant pi over 2 is 1. Cosecant squared is also 1. We still have the minus. So this is minus 1. All right, that's all I want to say about B2. And I'll move on to the last type, which is C. But before I do, I've got to erase this and see if anyone has any questions. Okay, so type C. This is a slightly different type of indeterminate form. I call it type C because most of the time it reduces to type B2, actually, and then you use that to get to type A. So it's sort of 2 steps of simplification. This concerns indeterminate forms that look like, let's see, I might as well write them in the same order I wrote them in the book. 1 to the power of infinity. Actually, plus or minus infinity will screw you up. 0 to the 0 hertz as well, and infinity to the 0 hertz. Those are 3 different types, but they all involve exponentials. So if you have 1 to a very large power, funnily enough, you think it'd be 1, but it's not. It doesn't have to be 1. 0 to the 0, well, that's clearly going to be a problem. I mean, 0 to any power is 0, but any power to 0 is 1, so what's 0 to the 0? And infinity to the 0, well, who the hell knows? Is that going to be 1? It could be anything. So we'll see some examples of each of these types. The first example I want to show you is the limit as x goes to 0 plus of x to the power sine x. So if you plug in 0 here, you get 0 to the power 0. So this is a 0 to the 0 form. That's actually the middle one of these forms. So how do you deal with this? This is kind of messy. Well, the solution, or the way to deal with it, the method for a type C, where you've got x stuff in the bottom, in the base, and the exponent. That's what type C is. So it's x in general, x stuff to the power x stuff. This isn't really about L'Hopital's rule. In fact, this works for any limit that's x stuff to the power x stuff. What you do is stop, resist the temptation to write equals. Instead, write down a new limit, which is the logarithm of the old limit. Hopefully this quantity is positive, but then again, exponentials always positive. So, okay, logarithm of x to the sine x. Let's just solve this problem. The beauty of the logarithm, of course, is it knocks the exponent down out the front. So the sine x comes whistling down outside the log, and you get sine x log x. Nice. Well, now it's just a type B2 after all. If you work it out, you're going to get 0 times minus infinity, but we're going to put one of these on the bottom. Again, avoid the logarithm, keep the log here, and put the sine down as a cosecant. So There's type B2. Now I've reduced it to a minus infinity over infinity case. Cosecant 0, after all, is 1 over sine 0, which is infinity because we're going from the right. So I can use L'Hopital's rule in its pure form. Derivative of log x is 1 over x. Derivative of cosecant x is minus cosecant x cotangent x. This is pretty similar to what we had before. Pretty similar to what we had. Let's just unravel it. These are now in the denominator. So they can come up to the numerator as minus sine x tan x. Whereas the x actually belongs on the denominator. This limit is 1. This limit is 0. So the product is 0. Are we done? No. We didn't find the limit that we were looking for. We found a different limit. We found a limit of the logarithm. So if you exponentiate both sides of this, you get that the limit of the actual function is e to the 0, which is 1. Seems a little bit crazy. I take e to this limit, and actually the point is that that's an exponential continuous function. So you can actually just bring the e inside there, and e to the log anything is itself. Another way of looking at it is, in general, if f of x goes to L, if log of f of x, rather, goes to L as x goes to some number a, then f of x goes to e to the L as x goes to a. So there's our general technique. When we have this stuff to the stuff, we take log of it, find that limit, get the answer, and then say that the original limit is e to the power of that answer. And that will work regardless of whether you use L'Hopital's rule. There's only one exception that you have to really think about. Suppose L was infinity. What would this be? Well, it's also infinity. I mean, e to the infinity is infinity. What if this went to minus infinity? How would you interpret e to the minus infinity? Yeah, it's 0. It's a sort of double limit, but if L equals infinity here, e to the L equals infinity, whereas if L is equal to minus infinity, e to the L equals 0, as far as this statement is concerned. It's all justified by the continuity of the exponential function, although I'm not going to get into the details. Okay, so all I have left is that I'd like to show you 2 more examples of type C, and that might be it for time. Let's see how we're going. Yep, 9:23. So 2 more examples, and then we'll be done. So next time, integration. So first example, limit as x goes to 0, 1 plus 3 tangent x to the power 1 over x. It's actually a nice example because I don't even need type B as it turns out. I'll show you why. First of all, plug in 0 and you get 1 to the power plus or minus infinity. Right? 3 tan 0 is 0, so you get 1. Power here is 1 over 0, which is either infinity from the right, minus infinity from the left, so it's definitely indeterminate. You can't just plug in the answer. So what do? Resist the temptation to do anything. Instead, or with that, start with the log of it. Ouch. Killer chalk. Log of 1 plus 3 tan x to the power 1 over x. Well, the 1 over x comes out the front. And actually, it's already a fraction. We don't even need to do this rigmarole of dividing. We can just rewrite it like log of 1 plus 3 tan x over x. And now, if you plug this in, again, you get log of 1, which is 0, over 0. So this is just a 0 over 0 form. We can use regular old L'Hopital's rule to say that this is the limit as x goes to 0. The derivative of log of something is 1 over that something times the derivative of that something. The derivative of tan x is secant squared x. All over 1. Now, if you plug in 0, cosine of 0 is 1. Secant of 0 is 1 over 1, which is still 1. Square it, still 1. So this is 3. This is 1. So this is 1 times 3 over 1. That's just 3, if you work it out. Limit is 3. Are we done? No. The log of the thing we want goes to 3. Therefore, raise both sides to the power e to the blah, both sides, and you get the limit as x goes to 0 of exponential of the log, which is gets rid of the log, is e to the 3. E cubed. That's the answer. Why is this equal to 3? I plug in 0. Do you agree? We get 1 over 1 plus 3 times 0. So this is just 1. That factor is 1. That's 1. And secant of 1 is 1. Secant of 0 is 1. So it's just a straight plug-in, but you know it's trig. So you have to be careful. All right. I have just a few minutes. One more example. I don't even have time to erase the top board. I have to go and get the example. Oh, it's just x to the minus, well, x to the minus 1 over x. Okay, if you plug in infinity this time, you get infinity to the power 1 over infinity is 0. Minus 1 over infinity is 0. So this, of course, is another type of indeterminate form. Start just by saying limit as x goes to infinity of log of this quantity, x to the minus 1 over x. This is a pretty quick one. You get minus 1 over x. So you get minus log x over x. And this is very straightforward. It's just an infinity over infinity L'Hopital's rule, as you can see by substituting. And you get minus 1 over x over 1. That limit is 0. So this immediately proves that after taking e to the both sides, you get limit x goes to infinity of just x to the minus 1 over x is e to the 0, which is 1, once again. All right, so here's the deal. In section 14.1.6, there's a summary of all of these L'Hopital rule methods in one place. And actually, in 14.2, there's a summary of all the limit techniques that we've done prior to that. And that actually completes everything that we know about or any type of limit problem that we're ever going to actually do, with only 2 exceptions to the end of Math 104. It's the end of the whole book. There's going to be one in a week or 2 when we do the fundamental theorem of calculus, but that involves integrals. And then the other one involves Maclaurin series, so that is much, much later. So then, next time, as I say, we will move into the rarefied heights of integration. So until then.